This table talks about challenges in the approach to nanotoxical, and we're going to talk about challenges and potential framework approaches to addressing nanomaterial risk assessment. Professor Ronald White, he is a professor in the public health, Johns Hopkins Bloomberg School of Public Health. He is also the vice director of science and risk of public policies, applications and scientific development in the public health, especially in environmental health. And this includes the effects in health associated to air and what is used in the public policies. He's an external consultant in the Institute of Breathing Lovelace, and he works with nanomaterials. He obtained his master's and PhD at the Clark University.
Thank you very much for the introduction, and I want to thank Dr. Wiseman and the organizing committee for inviting me and allowing me to participate, and for those of you who actually returned back from lunch, thank you. So I was asked to talk about assessing nanomaterial risks and some of the challenges and approaches that have been discussed in the literature about how we take on the challenges that we've heard about over the last day and a half in terms of trying to assess the very difficult problem of trying to grapple with nanomaterial risks and approaches. So what I want to do is first start out, make sure that we're all on common ground. Why do we worry about engineered nanomaterial risks? Well, we heard quite a bit already from this morning's session on some of the health concerns that might be associated with nanomaterials. We have relatively little information on the hazards, exposure, and dose response, although that's certainly improving as time goes on, but still compared to most other chemicals or pollutants, we have very little information. The size and shape similarities to pollutants or compounds that we're concerned about, such as ultrafine particulate matter air pollution, and their relationship to nanoparticles in terms of size, and carbon nanotubes and their similarities in terms of size and potential concerns with asbestos certainly is an indicator of why we might potentially be concerned. There have been potentially dramatic increases in potential releases and exposures via consumer products. And here you see information from the Woodrow Wilson Center for a Project of Emerging Nanomaterials showing the growth in consumer products that self-indicate that they have nanomaterials in them. It has essentially tripled in the last 3 or 4 years and seems to be on a linear progression. And as Dr. Rocco noted in his opening remarks, consumer products are only one aspect of areas that have nanomaterials, but it's one which has probably the greatest potential for public exposure and potential significant concerns in terms of health and environmental risks. And of course, as we've been discussing throughout the symposium here, nanomaterials have novel properties in terms of quantum effects, and some of the very real reasons why we are engineering nanomaterials is to give them these unique properties that make them so attractive for a variety of applications. But I think it's important to just reinforce that nanomaterials, which may very well be similar in composition to other larger bulk forms, aren't necessarily the same thing. And as was discussed by the European Commission's Scientific Committee on Emerging and Newly Identified Health Risks, that extrapolating from bulk materials to the nanoform is not straightforward. And in fact, that simply the reduction in size will change physical characteristics and the potential for biological effects. And I've added emphasis to some substances that may be deemed of low risk in bulk may well have significant risks in the nanoparticulate form. And the Royal Society, the UK Royal Society report noted that chemicals in the form of nanoparticles and nanotubes should be treated separately from those produced in larger form. And I reinforce this because there are some that have argued that, in fact, that just because substance is in nanoscale, given that we know what the properties are in the larger forms, we really don't need to be that concerned about it. And I would suggest that that's not necessarily the case. So just to reacquaint everybody with the key components of health risk assessments, and I'm going to focus on health issues, although I want to acknowledge that environmental impacts are potentially very important as well. And I'll mention one example of that later on in my talk, but I want to focus on health risks. That's the area that I'm focused on, and that's the area that I do research on, and I'd like to emphasize it. So there are 4 steps that are the traditional steps in health risk assessment. Hazard identification, and we've been talking about hazard identification quite a bit in the previous presentations. Exposure assessment, which is determining the extent of exposure. Dose response, which is the relationship of dose or exposure to some kind of health effect or health response in terms of a quantitative relationship. And then when you combine all those 3 pieces together, you have risk characterization, which is the probability and hopefully the magnitude estimate of the human health risk, as well as some description of the uncertainties that are associated with those health risks. So what's presented in this figure is one description of the environmental health framework for risk assessment. So the traditional environmental health paradigm, where you move from pollutant emissions to some level of environmental concentration in the environment, to which then the human is exposed, then is uptake, and there's a biologically relevant dose. That dose then interacts with macromolecules in the body to result in an adverse health effect. So this is the traditional environmental health paradigm that is often used. But when you look at some of the components that go into these factors, you need to have production information to calculate emissions. You need to know what's in the ambient environment, so you need environmental monitoring, and you utilize modeling where you don't have monitored data, which is frequently the case. You may use exposure modeling as well for exposure assessment in terms of, we have typically very little human exposure monitoring in terms of things like biomonitoring indicators, which are now becoming more of interest to people, but it's still an emerging field. And then the pharmacokinetic modeling, which you heard a little bit about earlier this morning, in terms of trying to calculate the relationship between where the chemicals are in the human body and how they ultimately can impact with an adverse health effects. Down here you have some of the approaches to assessing adverse health effects. Epidemiological studies are certainly considered an important, if not gold standard, because we're actually measuring effects in the actual human population. Animal data is often typically used where we don't have human data, as well as in vitro toxicity studies. And the area of QSARs, or quantitative structure-activity relationships, is certainly becoming more utilized as well, and I'll talk a little bit more about that as well. So all of these components certainly go into the exposure quantification and then effect quantification in terms of health effect. You need to have exposure and hazard, as was discussed earlier, and that provides you your risk assessment. So what are some of the challenges that we've got in terms of assessing nanomaterial risks and the inputs to this risk assessment process? Well, one of the key questions is, how do we define nano? And we've heard this again, as well as a volume definition. Is it based on the structure, on the properties, which we've heard are so important in terms of defining nanomaterials? What about this issue of for nanoparticles, while we focus on single nanoparticles, very often they don't remain as single particles for very long. We have to deal with the fact that ultimately what people are being exposed to may often be agglomerates or aggregates. There's the issue of transformation, especially for very reactive nanomaterials in which they're photoactivated and transformed. And then one issue that I haven't heard much about is the issue of purity, and that is that even most nanomaterials aren't necessarily pure in terms of the composition, that in fact for a lot of the commercial nanomaterials there are a lot of impurities, and we need to recognize that when we're worried about assessing health risks. How do we measure exposure? Is it based on mass, which we've heard is probably not a very effective way? We've heard discussion about particle number, and that's often used for ultrafine combustion products now. In terms of ultrafine particles, we usually refer to particle number. Should we be deciding exposure based on surface area, which we know is an important component? So we also have problems with low limit of detection methods, and we need to certainly improve our ability to detect nanomaterials in the environment and certainly in the human body. And how do we, this issue that I think was mentioned earlier today, how do we distinguish the engineered nanomaterials from background nano-sized particles? And that certainly complicates doing exposure assessment. We have lack of information on fate, transport, and uptake, absorption, distribution, metabolic activity, and excretion. What's the impact of solubility, coating, surface charge, et cetera, on bioavailability, translocation, and toxic effects? We've had some discussion of that already at this meeting. These are all important issues that we need to consider as we decide how to assess nanomaterial risks. So there's a lot of uncertainty, and there's certainly a tremendous amount of variability, both in the types of materials that we're dealing with as well as in their application. So we're really dealing with two kinds of concerns. One is, as we look at the potential pathways for exposure, we're concerned very much about the workers who are involved with producing nanomaterials, but we're also concerned about the consumers who ultimately will be exposed to the results of the products, both in terms of their use, but also in terms of their waste disposal. And I'll talk more in a few minutes about life cycle approaches, because I think this is very important. We need to not just worry about how people are being exposed initially, but also what happens to these products after they're being disposed of. So in terms of assessing the toxicity of nanoparticles, I want to just very quickly go through this. We've heard quite a bit about this already at the meeting. There are in vivo studies that show increased deposition compared to other particles, altered clearance, inflammation, oxidative stress, fibrosis and granulomas, death in animals, translocation to other organs, including the brain, and precancerous lesions. In vitro studies, we've got genotoxicity results, again, oxidative stress, inflammatory responses, which we heard a little bit about in terms of skin, increased cell death, alterations to the cell cycle, and penetrations of the various barriers, which results in concerns. But there's a potential for other kinds of effects that we need to start thinking about. This is a study from Zhao et al. From 2005 looking at fullerenes, C60, and this is a computational modeling effort where they modeled the effect of the uptake of these fullerenes in DNA, either through the microgroove or through the ends of the DNA in the hydrophilic ends here, and basically saw that it had the potential to alter gene expression and potentially change the structures within the cell. So certainly some potential reasons to be concerned. So what are some of the approaches that have been taken to address these concerns and come up with an approach to assessing risks for nanomaterials? There have been a number of approaches that have been suggested. I will sort of take you chronologically through some of the approaches that have been discussed. We'll talk about influence diagrams and life cycle analysis, some of which include expert judgment, some bridging toxicology that you've already heard from Dr. Warheit, high throughput screening, and predictive toxicology, both structure activity and quantitative structure activity relationships, and read-across approaches. So one of the first approaches that appeared in the literature was an article by Dr. Kara Morgan at the U.S. Food and Drug Administration, who proposed a nanoparticle risk assessment framework. And here you see, this is essentially an influence diagram approach that utilized expert judgment to try and discuss the relationship of these different components. So here are the particle characteristics that are related to the product and its use, and whether or not then you see it in the environment, so is the presence of it, and then uptake, transport, and fate, all of these being part of the exposure component, and then toxicity, toxic effects, transport, and fate, leading to both human health risks and ecological risks. And of course, time is a factor in all of these. So each of these components were then broken out into subcomponents. I'm going to just show you one example. This is the toxic effects module. So again, this is this module right here with much more detail. And here you can see the various components. So you have particle size, absorption, surface coatings, reactivity, and composition, all impacting the potential for cellular and subcellular changes. And then a variety of impacts or adverse health effects that might occur, both in terms of the results of these, all leading then to having an impact on human health risk. And the arrows basically indicate where you see an effect relationship between the first item and its impact on the adjacent piece. So nanoparticle risk assessment frameworks, this was a result from a Society of Toxicology symposium that was held in 2005, I believe. They identified the key pieces of risk assessment, so under hazard, chemical composition, particle size, structure and properties and coatings, exposure assessment, particle behavior, its uses and durability, receptor impacts and routes of entry, toxicity, you have ADME, reactivity, and dosimetry, all then combining into the likelihood of effect, the nature of the effects, and how effective potential controls are. So again, sort of laying out some of the key concerns. Kandlikar published a piece here. Again, this was in the context of using expert judgment. So this is where you go out and you ask experts for their best judgment and opinion on the potential relationships between these factors and the key components that are of concern in terms of assessing risk, as well as the potential mechanics by which nanomaterials might affect health. And here you see them laid out. Here again is the typical environmental health paradigm and how nanomaterials and nanoparticles in this particular case are relevant to the key components of the environmental health paradigm. You've already heard about the Environmental Defense DuPont Nanorisk Framework from Dr. Warheit, so I won't go into much more detail. I think one of here's the evaluate risks. So here's where risk assessment comes into the process, and then you manage the risk and then respond. I think one of the key interesting things here is also the importance of iterating information, so you feed back, and you'll see this in some of the other examples that I'm going to mention in a few minutes, and that you also assess, prioritize, and generate data, and then that also feeds back into the system. So I think it needs to be a continual feedback process where the information that you're developing, the hazards that you're assessing, are then reevaluated based on new information. This is an approach by Sweet and Strom that lays out the integration of lifecycle methodology. In lifecycle methodology, you were basically looking at the potential impacts of nanomaterials across from the manufacturing process and from actually getting the initial components of nanomaterials through its production, its use, its disposal, and then what happens to it after it's been disposed. So here you have the traditional life cycle. You've got product design, manufacture, distribution, use, and end-of-life components, including recycling. And here you have, again, the typical risk assessment methodology. And here we're basically talking about integrating the typical risk assessment methodology approaches with a life cycle methodology. And that's been actually proposed in a number of arenas. Dr. Michael Davis at US EPA proposed a similar concept of integrating life cycle analysis with risk assessment. Here you see it laid out a little bit differently, where you've got the life cycle stages here, from feedstock to manufacture, distribution, storage, use, and disposal, but then laying out the different environmental pathways that may be of concern, the fate and transport, both the primary contaminants, but also I think it's important to note that there'll be secondary contaminants. As nanomaterials enter the environment, there are transformations that take place. There are chemical transformations, there may also be material transformations. And then exposure both to the human population and to the environment and ecology, leading to effects in the ecosystems and in health. Joanne Shatkin at the Conservation Law Foundation Ventures proposed this framework, which she called a streamlined life cycle risk assessment approach, where, again, here's the life cycle process, but you work primarily on identifying upfront some of the hazards, and then really the emphasis is on assessing exposures. And again, a very iterative process where you then evaluate toxicity at its use, but then feedback information so that you're integrating new information into this process. So life cycle assessment that I've talked about and that a number of these frameworks refer to is a fairly complex process for nanomaterials, and I think this diagram from the EPA Nanomaterials Research Strategy just gives you some idea of some of the challenges that you have in terms of dealing with life cycle analysis in terms of nanomaterials. So you've got all these different components in terms of material selection. You've got different manufacturing processes, either top-down or bottom-up, wet or dry. Is it dispersive or a composite application? And where is it being used in environmental remediation, medical products, or manufactured goods? And then what happens to it upon disposal? Is it recycled and then remanufactured again, or is it put in a landfill? Is it incinerated? Does it go through water treatment, and does it bioaccumulate? So there are some significant informational challenges that we have in trying to do life cycle assessment. And here are some of the science issues for each of these stages that we've just been talking about. So one example of where life cycle analysis has been done for nanomaterials, and this is done for carbon nanofibers and compared to several different kinds of other materials. So here you see you need to calculate the energy use that goes into the manufacturing process, as well as the type of material, how is it extracted and processed, its production, its use, is it recycled and disposed of. So here's the life cycle process. And then look at the actual emissions in terms of pollution and so on, and then waste. And then try and assess this as an output. What Bakshi and et al. Found was it was very difficult to do this for emerging technologies because, frankly, the data was not there. They had to really struggle and make a lot of assumptions for a lot of this data. But here's the results of their assessment. And they used both carbon nanotubes manufactured with methane or ethylene and compared them to aluminum, steel, and polypropylene. Now, this was on a same mass basis, which may or may not be fair because hopefully nanomaterials would be used in lower volumes. But for same mass basis, they basically found that in terms of disability-adjusted life years, which is basically made up, for those of you that are not familiar with this term, of years of life lost plus years of life disabled, and those combined give you disability-adjusted life years. So you have disability-adjusted life years per kilogram of material on this axis, and here you see the effects. You have ozone layer effects in terms of ozone layer depletion, radiation, climate change, inorganic respiratory effects, organic, and then carcinogens. And clearly you see that carbon nanotubes, by whatever manufacturing process, have potentially more significant human health impacts than aluminum, steel, or polypropylene. And here they also assessed the environmental impacts and found that in terms of potentially disappeared fraction, which is the impact on species depletion, that again, carbon nanotubes compared to aluminum, steel, and polypropylene had a greater impact, especially on acidification and eutrophication of water bodies and less so on ecotoxicity, as you can see here. So I've mentioned expert judgment, expert elicitation a number of times, and that's because we really have so little information on a lot of the components of these risks that we often need to now rely on the best educated judgment of experts in these fields. And this is an article by Wardock et al. In which they looked at a number of different materials that had nanomaterials, batteries, field emission displays, sunscreen, air freshener, toothpaste, MRI contrast, food supplements, and tennis rackets, all of which had different kinds of nanomaterials. And based on these expert judgments, expert elicitation, which is a very formal process of asking experts to weigh comparatively their risks, they looked at risk information, what data was missing, and asked them to rank in a relative way some of the concerns about exposure, which is on the x-axis, and hazard on the y-axis. So you can see, for example, the nanomaterials in batteries was relatively low by these expert judgments in terms of both exposure and hazard, whereas while MRI contrast might have been high on exposure, it was relatively low on hazard. But sunscreens were relatively high on hazard, even though they were sort of mid-level here in terms of exposure. And this is air fresheners here and toothpaste here. So these kinds of applications, air freshener, toothpaste, and sunscreen, which is where consumers are likely to most interact with these materials, came out the highest in terms of a combination of exposure and hazard or risk. So there are a number of particle toxicity testing challenges. We've heard about those already from other speakers, including here a quote from Dr. Warheit's article, that we, in terms of providing predictive screening data, we're going to need better information, and that was also the view of the European Union Commission Scientific Committee. Some of the mechanisms that have been proposed for nanomaterial toxicities are laid out here. And I don't have time to really go into them in detail, but they really relate to inflammatory responses and some of the components, effects on membranes, macromolecules, enzyme activity, and gene expression. Dr. Warheit talked a little bit about comparing quartz and some of the other particles, so I won't go through this, except to say that these kinds of comparative toxicology studies are certainly going to be one approach to trying to get a better handle on nanomaterial toxicity. High throughput screening, this is from Andre Nell and his group in Southern California, looking at oxidative stress as the key outcome and model of concern, and looking essentially at different tiers of oxidative stress response, basically saying that there's probably some role for high throughput screening based on oxidative stress, but I think it's clear that that's certainly not the only mechanism of concern. So it may only be part of the answer. Quantitative structure-activity relationships, in which we actually try and quantitatively predict from one material to another, is another approach. This is an article from Zia et al. Listing some of the key pieces of what we have to worry about in terms of trying to come up with this QSAR approach for nanomaterial biological effects. And as you can see, there are a lot of key things that we've already discussed at this seminar that need to be considered in terms of surface chemistry, in terms of crystallinity, photoactivation, surface charge, some of the very things that we've talked about. These are very specific issues that we will need to have much more data on in order for us to be able to use this predictive approach. And in fact, the European Commission Scientific Committee again said that successful application of QSARs is dependent on the ability to derive properties of new nanoparticles from its atomic molecular structure. Such models are plausible, but they represent a significant challenge in toxicity. So I think it is certainly one way that we will be beginning to address this process, hopefully from a screening point of view, but certainly we will need much more information. So future challenges for nanomaterial risk assessment and risk management. Dr. Rocco spoke yesterday about the 4 generations of nanomaterials This is from the IRGC, the International Risk Governance Council's Nanotechnology Risk Governance document from 2006. And I think, we are certainly, we have entered the second generation, as Dr. Rocco mentioned, where we're moving from passive to active nanostructures. We're probably at the beginnings of the third approach of integrated nanosystems, and the fourth approach of molecular systems is certainly ahead of us. My point here is that given the data gaps that we have for the first generation materials, and I think everybody will acknowledge we certainly need a lot more information in terms of assessing risks, public health and environmental protection policies will be constantly in a catch-up mode as we're now trying to deal with second generation and now emerging into third generation. So we are already, I think, behind the gun in terms of trying to understand what the potential health and environmental risks are from first generation nanostructures, and if we don't invest tremendously in this effort, we're going to continue to be behind in understanding the risks from these future generation products. So the key concepts that I want to leave you with is that the risk assessment frameworks for nanomaterials is really going to require an integration of the classic risk assessment paradigm, the 4 steps that I discussed at the very beginning, with life cycle analysis and probably expert judgment for quite some time in the future, just because of the lack of data. We need to see an increased emphasis on exposure assessment and the development of exposure biomarkers, because as has been discussed here also, if there's no exposure, there's no risk. We need to develop and refine screening approaches to prioritize hazard assessment, the concept of green nano. Can we now engineer ahead of time nanomaterials that we think will be less toxic, have less of an impact on the environment, and certainly focus on the research needs that I've just discussed and generating the data that we need. And then also, do we need to now start to think about the potential risk and benefit trade-offs as part of the risk assessment process? Because clearly, as we've heard, there are a lot of very beneficial medical, environmental remediation applications for nanomaterials, but there are also potential health and environmental risks, and we need to think about how to integrate those risk-benefit trade-offs or risk-risk trade-offs into our thinking. So with that, I'm going to just hope that we are not undecided as scientists and as regulators about the need for nanoparticle regulation. I think it's essential. It has to come. The question is, what form will it take? We will hopefully not be ostriches with our heads in the sand looking for a loophole, but we'll actually start moving forward as we develop nanomaterial risk paradigms. Thank you very much, and look forward to the question period.